Good morning. My name is Vinod Sharma and I have over 13 years of experience teaching physics to senior secondary students. I have worked with many different boards including CBSE, Cambridge, IGCSE boards as well as JEE and NEET institutes as well. And my focus has always been on building strong conceptual understanding along with the problem solving skills. In this demo session, I'll be teaching the topic work, power, energy, which is very important concept in mechanics. And I'll begin with the basic ideas and then solve few problems to show how these concepts are applied in real life situation. So let us begin with the concept of work and energy. Let's start with the energy only. Energy is what? It's the capacity of doing work. So let's move to the next slide. Here, as we can see that work is a form of energy. It's written over here. Work is a form of energy over here. Sorry, I'm not able to write onto this page. If I'll choose another pen. Okay, sorry for the interruption caused. I'll move to the previous page and here only I'll select different page. Okay, fine. Work is a form of energy, and energy tells you the capacity of doing. It tells you the capacity of doing work, the ability to do work. So what sort of work we are going to talk about here? We are going to talk about the work itself only. So work is done by a force F on mass m when the force and the displacement delta x are parallel. It is trying to say. It is trying to say that suppose if we are having any object whose mass is m, okay, and here it is kept over any other surface like this, and some amount of force has been applied. Let's say here a force has been applied along with the horizontal we can see theta angle is there. So suppose if the force is applied in this at an theta angle, then we can see a displacement would be there in this very direction. Means after, let's say that if at t is equal to 0 the object m was here, then after t time the object has been displaced from its position and it has traveled some distance over here. If you can see, it has traveled some distance. So then we can say that the work is done over here. What I'm trying to say, that when a force acting on an object and the object is displaced from its position from the point of application, then work is said to be done. Okay, and here if the displacement, if you'll see the displacement, then the displacement here is S displacement is done. So what I'm trying to say, that work is done by a force which is equal to the scalar product of the applied force and the displacement of point of application. Here I'm trying to say actually, like here if I'll write about the work done, so work is equal to force has been applied and the displacement is there. In general, in grade 9 we used to write like this, but here we can see that actually that the component of force is acting in the direction of the displacement. So the component of force in the horizontal direction is F cos theta, and in the perpendicular direction it should be taken as F sin theta. So we can see that the displacement is in the horizontal direction and the applied force is parallel to the displacement over here. So I can write it as F cos theta into S. So actually this is the dot product F dot S, or we can also write that W is equal to F S cos theta, because for can we say that in the direction of the applied force, the component of this displacement here is acting? So it should be S cos theta acting in this very direction. So yes, we can write W is equal to Fs cos theta, and as it is a dot product, means the displacement and the applied force both are in the same direction, so it's a scalar product. It's a scalar product. We know what is scalar product is. Scalar product means which are having only magnitude and no direction is there. Okay, so clearly we can see that the work done here is what? Scalar in quantity. Here few things are written, that W is equal to F delta x if delta x and F are parallel. As we can see that the applied force and the change in the displacement, here instead of S in this PPT it is written delta x, means what? The change in the displacement, both are in the same direction. That is being written over here. If I'll move to the next page, we can see, let me first rub all these and we can talk about the types of forces. So let's talk about the types of forces first. Like if work done and the displacement both are in the same direction, then the work done is said to be positive nature. Then the work done is said to be of positive nature. What I'm trying to say, let's suppose if I'll draw that the types of work that we have got, the types of work done. Types of work done here. So if I'll write, okay, let me change the color. So here we'll have generally 3 types of work done. One is positive work done. One is positive work. Second is negative work. I'm just writing it in short. Negative work, and here it should be zero work. Here it should be zero work. Let's talk about how it is positive and how it is negative. So in quickly we can say few things. That suppose here if the angle is positive, means in this case if the angle is acute angle from here to here, if the angle is positive and acute angle, if it is acute angle, means it should be more than 0 degree but less than 90 degree. Okay, so in that case it should be what? 90. It should be less than that. Theta angle should be less than 90 but greater than that of 0 degree. In that case work done is said to be positive. Okay, second case if I'll draw for negative work done, let me draw separation over here. That if in this situation, if it is in the second quadrant, when it is coming from 90, when it is coming from 90 to 180 degree, this is the second quadrant. Here we can see that the angle that has been subtended, here the angle which has been subtended is what? It's greater than 90 degree but less than 180 degree. In that case we will have W is equal to Fs cos 180 degree, and here the work done is said to be negative. And in the first case what we got, that work done is equal to Fs cos 0 degree I'm just giving you the example, not exactly 180 degree. It should be more than 90 degree and less than 180 degree. Okay, and here it should be more than 0 degree and less than 90 degree. So here the work done is said to be positive. Similarly, in the third case, if I'll draw the third case, in the third case, 0 work done means if the work done, if the angle is totally 90 degree, if the theta is 90 degree, in that case we can write it as that work done can be written as Fs cos 90 degree. So work done is said to be totally 0 over here. I'll try to give you a few examples relating this. Let's suppose we are having a shape like this. Okay, and in this very shape, if tension is acting in this very direction and if its mass is m, then mg is acting downward. If mg is acting downward, then here tension will act, and in this given situation, if this body is going up only with acceleration a, fine, so let's say positive way. So if it is going, so what is the work done by the tension over here, and what is the work done by the gravity here, if and what will be the net work done over here, that we can find it out. So let's find it out. As we have got that if the work done and the displacement, if the force and the displacement both are in the same direction, then the work done is said to be positive, and the angle should be more than 0 degree and it should be less than 90 degrees. So in this case, work done by the tension, you can see that it's going up only, means in the direction of the tension only it's moving. Can I say that this is positive work done? So answer is yes. Why? Because the tension is acting in the same direction and the acceleration both are in the same direction. So we'll talk about the work done by the gravity. You can see that the gravity acts downward and acceleration means the net force, the force acting on the body is opposite to that of the gravity. So can we take it as negative? Why? Because here the displacement and the applied force both are in opposite direction. So here what would be the F net? What will be the net work done over here? So we can see that F net can we find it out using T minus mg. So T minus mg, we are going to get positive work done over here only. Clear? So let's move ahead and talk about the negative work done that we have done over here. Keeping all these things positive, negative and 0 over here, we'll use as a reference, and then we can move ahead. Let's suppose again the same condition, one same body is kept over here. Okay, and here we are having tension acting in this very direction and mg is acting in this very direction, and in this given case the body is accelerating in the opposite direction, in the downward direction, let's say, and yet it is positive in nature only. So what should be the work done over here? So here the work done by the tension, work done by the gravity and the net work done. Let's see what it should be. We can see that the tension is acting in the upward direction and the mg, the weight of an object, is acting in the downward direction, as well as the acceleration is in the downward direction. So here tension and the acceleration both are making an angle 180 degrees. So it should be negative because the applied force and the displacement both are opposite or in opposite direction. So work done by the gravity, you can see the arrow is in this direction, and for the acceleration both are arrow in the same direction, so making angle 0 degree. So it should be positive work done. And can you tell me that what would the F net acting over here? Will it be positive or negative? So it should be, I guess, positive only. It should be written as mg minus t in this case. Any guesses for the 0 work done? Yes, the formula should be Fs cos 90 degree. Okay, like if the same situation, like if the same object, okay, whose weight is acting downward, means mg is acting downward and tension is acting in the upward direction, and this body is going up, let's say with a uniform velocity, with a uniform velocity. I guess students, you know, if any body moves with an uniform velocity, then the acceleration would be 0. If the acceleration acting on a body is 0, then in that case we can say that the F net acting on a body is 0. So no force is acting over here. So here the work done by the tension will be positive, work done by the gravity would be negative, because as the tension and the uniform velocity, it's going up only, so it's moving in the direction of the tension only, it should be positive. But for the, you can see for the gravity, as it is acting downward, but still the body is going up, making an angle theta is equal to 180 degrees, so it should be a negative work done. But overall its work done is what? 0 only. I hope you have got the students. Let's move to the next page. Let me rub this first, then we'll move ahead. Here we have got some situation. Suppose here M1 object is kept over M2 object. Okay. If the object is kept in such a way that here it's kept over a horizontal rough surface. If it is kept over a horizontal rough surface, so we will apply a force. I'll use this color over here. Okay, let's change different color. If I'll apply a force F over here, then what will happen? A frictional force will comes into the play, which will act in the downward direction. Let's name it as F2. Why? Because it is acting in the second object. Okay. Due to this frictional object, there should be, and we can see that both body are sliding, like both body are moving together. Here it's a situation that double block system and both are moving together. If both are moving together, obviously, so here in this direction, like due to this, a frictional force F1 will act in this direction, and to oppose it, due to this third law of motion, F1 will act in this very direction only. Is it clear? So if I have to find that for M1, let's change the color of the pen and then we'll talk about everything in detail about, like for M1 and for M2. We'll talk about all these things. Okay, let me rub this. Okay, so for M1, what should be the work done? It should be the work done by the F1. Don't you think that both are moving together, because the applied force is in M2, but M1 is also moving along with the M2. It means there is a frictional force in between M1 and M2 which is letting it to move, and that friction is what? F1. So here you can see the applied frictional force is letting the body move in this very direction, and the displacement is also in this very direction only. So here the work done by the F1 will be taken as positive. Say yes or no, students. I hope you have got this. Now the second, for M2, if I have to talk about for M2, if I have to talk about the M2, don't you think that for M2 the frictional force will be F2? Yes, obviously. So the frictional force is acting in the opposite direction, that but through the pink color you can see it, and here the body is moving in this very direction, making a 180 degree angle. Both are the applied frictional force and the displacement, both are in the opposite direction. Don't you think it should be negative? Yes. Now if I have to find the F net acting on the body, you can see that the displacement still in this very direction. So here it should be positive work done. I hope you have got this, students. Isn't it? Any problem till here? If no, then we can move ahead and we'll talk about one more situations. Like suppose if you have any table like this, and over this table, if I'll keep if I'll keep any circular string and a mass is kept over here, a mass m is kept over here, okay, and it's taking a circular motion in this very direction. So this will be the direction of that very thread that is moving. So in the particular, in a given instant of a time, don't you think that here, that on the very m mass, mg will act downward as it is kept on the table. Due to the third law, it will have a reactionary force the normal force acting upward. So n is equal to what? Mg we are going to get. So if I have to talk about the work done by the tension force, work done by the normal forces over here, as well as work done by the gravity. So here the work done by the tension, how much it should be? Do you have any idea, students? How can we talk about that? What should be the work done over here? Anything that we can see over here? As we can see that where, just try to find out that where the tension is actually moving, is actually showing, and then see that in which direction the normal force is acting. After that, check out the gravity is in the downward direction, as well as where the object has been kept. So when you will see it, as you can find out many of the things using this. You can find a lot of things, students. Like first of all, that the tension of an object is acting in the upward direction, isn't it? And the displacement is horizontal. So here they are making an angle 90 degrees. So Fs cos 90 degrees is equal to what? 0 only. As well as the normal force which is acting perpendicular, and if the table is perpendicular, if the displacement is perpendicular, because this is a table, this is the normal force, and this is the table. So here in this direction the displacement is, so it should be again 0. For the gravity, you can see the gravity is acting downward, and the displacement again is in what? This very direction. So making angle again 90 degree. So Fs cos 90 degrees. So the work done would be again what? 0 only. Fine. Same thing if I'll give you one example of pendulum. Suppose if you're having any mass which is subtended from a string, and it is being displaced from its position at a theta angle, and it will gain some height till here, and due to its periodic motion, it will come back in this very direction. It will go from here. So at any instant time, what should be the displacement over here? At any instant, the displacement would be like this, the tangent. But here what is acting? The tension force is acting. So along with the tension force, the angle, can you see this is 90 degree? Here also the displacement is in this direction, the tension is acting in this very direction. So the angle both are making what? 90 degrees. So here also the work done by the simple oscillating simple pendulum, the work done would be how much? 0. I hope you have got this, students. So let me rub this first, then I'll move ahead. Then we are going to talk about the work done by the gas on a cylinder. What we are going to talk about, students? We are going to talk about work done by the gas on a cylinder. Let me rub it first, then we can move ahead. Okay, here let's talk about this scenario. You can see here is a piston, and this piston has been compressed earlier to a dx distance. Earlier you can see the gas is inside it over here, isn't it? So what happens, you can see that now it has been, the gas has been expanded, means the work done has been done by the gas. So can we say that when a gas expands against the pressure, it does work on the surroundings. Here work done on the surrounding. So when the work done is done on the surrounding, and the volume has been increased from V1 to V2. So here the work done can be given as integration of P dV from V1 to V2. Here dV is what, the small change in the volume due to the expansion of the gases over here. So if any condition is given, that if the pressure remains constant, so then work done can be given as P V2 minus V1. So you'll get P delta V over here, students. And if, what will happen if the volume is constant? If there is no change in volume, if the volume remains constant, then in that case we can say that work done would be what? 0 only. So if there is no external pressure, then no work is done. For example, when a gas expands freely in a vacuum, no work is done by it. I hope you have got this, students. Let's move to the next slide. So we are going to talk about the concept related to the work over here. First of all, let's talk about all these ones. The work is defined over an interval. So here, the key idea, what is it? The work is defined over an interval. Therefore, there is no concept of instantaneous work. Means what? The work is not determined only by the initial and the final position. It depends on how the force acts during the motion. Work is calculated over the entire displacement of an object. Means what? I can write it as that work done is equal to force into displacement. Second point, like here, when several force acts on a body, the work done by a particular force is independent of the other forces for the same displacement. Here, like when we talk about that, when many force act on an object, the work done by one force depends only on that force and the displacement, not the other forces. Like suppose if we are having the work done by total, so it should be like the sum of all the work dones. It should be sum of all the work done like this. Okay, just like imagine pushing a box on the floor. Okay, so you applied a force, that is a forward force you applied, and the friction which is acting in the backward direction, normal force which is acting above, gravity which is acting downward. So each force contributes. Like here, if you are having any object, you have applied a force in this very direction. In this opposite direction, frictional force will come, and in this very direction, normal force will act, and in the downward direction, gravitational force will act. Okay, so here each force contributes its own work independently over here. Okay, so here the condition, the third one, the conditions for maximum and the minimum work done over here. So the force does maximum positive work. So it depends upon the formula is what? Fs cos theta. So when a force and a displacement are in the same direction, then theta is equal to 0. So like pushing a trolley forward, Okay, second case, when you will have the theta is equal to 180 degree, we have already discussed, like the friction acting in the opposite direction. I hope students you have got this. Let me rub all these. And we'll move ahead. Here is the work done by variable forces or the varying forces. Let's talk about this also. Okay, so first of all, earlier whatever we were doing, whatever we have talked, what we have understood was all about the constant forces. So here we are going to talk about the work done by the variable forces. You can see work done by the variable forces. So when a variable force acts on a body, the force change in the magnitude or direction during the motion, as well as the work done by a variable force can found graphically like this, the force displacement graph. Okay, like if the graph is a straight line, the work done equals the area of the geometric shape, whatever it is. Okay, so like if force increases linearly from 0 to f, suppose if we are having any spring like this, isn't it? So and you applied a force in the opposite direction, let's say of 1 Newton. So the body has been displaced to 2 centimeter. Then the next scenario would be like all the springs will come pretty closer, isn't it? Now do you think that if you apply the same amount of force, will you be able to push it? Maybe not. Why? Because they are now more closer. Then you have to apply, let's say 3 Newton. So by applying 3 Newton, you are applying, you're squeezing further, isn't it? Now if you have to increase, displace it, then you have to apply further force, let's say 4 Newton. So what you are doing, you are increasing the linearity from 0 to f over displacement. So for such type of work done, we have this approach of doing. So the work done is just equal to the area under the curve. Like here in this area, in this force displacement graph, you can see that delta x is given, means what, just like here as I have written 2 centimeter, so delta x. So area, so work done is equal to what, f delta x. Okay, here. So or you can also write it as that summation of xf initial to final of fx delta x.